Hey, this is Leach with Simpson Math, and in this video, I'm going to be going over some properties of the expected value of x and the variance of x, or basically what happens when we start manipulating them. In a previous video, you should have seen me talk about how to find the expected value and the variance using like a bit of a process by hand, but typically using Desmos or Excel or the 84. But this is going to be when you're already given or you've already found the expected value of a particular variable or set of variables, but we're going to start adding or multiplying or doing some different things. So let's get started by looking at how we might be manipulating these things. So first up, we could add a constant. So adding a constant meaning this c, so let c be just some constant. This is representing some number. So where x is a random variable, we don't know which output we're going to get. We know which outputs are kind of likely and what the outputs might look like. This is a constant, so it's always going to be a number. It's going to be the number 5. And it's not going to change for a particular problem. We're just going to add a number. An example of like roulette. Let's say you were to play roulette, and then you knew that no matter what was going to happen, you were going to tip the croupier a chip. And so then you were always going to have a minus, let's say 1, because you're always going to tip the croupier a chip. Was your plan. So even if you lost, you were going to give the croupier a chip. So if you did that process over and over, on average, you would be losing that one chip every single time. It's a fixed value. But if I'm subtracting 1 every single time, notice what happens for spread. It doesn't change it at all. The way I like to think about it is not so much in terms of probability world, but even just in terms of just data values. So if I had a classroom full of students and I said, oh, let's measure our height. And so we measure our height. And then go, okay, I have a 1 foot 12-inch box. Let's everybody stand up on that box, and now let's measure your height from the floor. Well, all of our heights are 12 inches taller, so we would be adding 12 to our mean, to the expected value. Well, what would happen to our spread? Well, if everybody is precisely 12 inches taller, we're not any more spread out. Think about the distance from the smallest to the biggest. Did the shortest person and the tallest person get further away when everybody stood up on a box that's 12 inches tall? No, we all stood up on the same box. We're all that much taller, so we're not any more spread out. So this kind of throws some students because you're like, but we're adding and it doesn't change anything. No, it changes our like data values, or in a way it changes the outcome that we're expecting of the random variables, but it isn't changing the spread. It isn't changing the relationship between those values. We'll see an example of that in a second. Right? If I'm multiplying by a constant, then, so again, let a, and this is not just a as in just like the article a, like a and the, this is a, like, so let the letter a, so put air quotes around it. So let a be some constant. So if I'm multiplying a times my random variable x, well then, if I want to find what the mean of that random variable is going to be, this kind of new random variable, then I can just kind of pop that a out. I can pull that a out and then multiply. I know that's kind of weird, but it's a bit of a shortcut. So the idea here is, again, let's say I had let me finish. So again, if I'm multiplying a times my variable x, how would that change my spread? Well, if I'm trying to find the variance, this a can come out, but it needs to come out as a square because this variance is a squared world. The standard deviation, the a can just come out as well, but we do need to make sure that it's positive. So I'm going to throw the absolute value of a around that. An example of this, again, I'm going to take everyone's height. We do that, and let's say record it in inches, and I go, I have some friends across the pond in England, and I want to send them our heights. So I'm going to let's convert all of our heights from inches to centimeters. So we multiply our height and our accurate inches with all these decimal places. We convert it with, I think it's multiplying by 2.54, which for, here at Temple College, that's our area code, 2.54. If we do that, well, the spread is going to change. So think about just the distance of the shortest person to the biggest person. Well, the shortest person's, your height's not going to change, but the number is going to change. The value of the number is going to change. So, let's say someone has, I'm just using easy numbers. If your height was 10 inches, something's height was 10 inches tall, multiply it by 2.54. Now it's 25.4 inches. But let's say something was 100 inches tall, and so I multiply that 2.54. Now it's 254 centimeters. Your height hasn't changed, but the number on the scale has, and the distance between those values have spread out. And so that will affect that. So that's it. So an example would be this. So I'm going to play our corner bet example. Again, if you're I'm referencing our example from the previous video about placing corner bets. So if you're unfamiliar, go back and check that one out. So I'm going to place a corner bet in roulette. But instead of placing one $1 corner bet, I'm going to put two $1 chips. So in the same spin, not multiple spins, on the same spin, I'm going to put $2 on it. So two $1 chips. So I can do that. I can basically accomplish this math by multiplying my bet by 2, basically the payout by 2. The reason why we might do this is, well, I've already worked hard to figure out the expected value, the variance, the standard deviation of our expected value of x, if x is my corner bet, in a $1 corner bet. But now I want to do, well, what happens if I put $2 on it? How much change should we expect this to be? So I already have these numbers. I don't want to have to redo the math for that. So I can just follow the formulas we just did. So I don't know what the expected value of 2x is, but I know we have a property up here that says if I have a constant of, let's say in this case 2, I can pop it out and just do 2 times the expected value. So I'm going to do 2 times my expected value that we got earlier, and it's a little bit more than a dime. All right, what about my variance? Well, I don't know the variance of 2x is, but I do know that I can pop out that constant as a squared of that constant. So I can multiply that constant as a square. So I'm going to pop out that 2, and we get 2 squared. That times the variance of x. Oh, I do know the variance of x. I found that earlier. So I'm going to do 2 squared, which is 4. 4 times my 7.62 and get this 30-ish. Again, for the standard deviation, I need to find the standard deviation of 2x. I don't know what that is, but I do have this property that says I can pop this a out as the absolute value of a times my standard deviation of x. So let's do that. So I'll pop that 2 out as this absolute value of 2, which will just be 2. And standard deviation x, I do know what that is. That's 2.7620. Do that multiplication, and I get 5.524. Do note that if I square rooted my variance, I would have the standard deviation of 2x. Or, of course, if I took this and I square it, squared that number, then I would get that 30. All right. Place a little tack in here, a little placeholder, a little thumbtack. Place a pin in it. That's the phrase. Place a pin in this because we're going to come back and compare it to something slightly different in just a second. So let's talk about the addition rule for the expected value. So this is not, I'm going to do something twice. I'm going to add a constant. Now I'm adding another random variable. A classic stat problem that pops into my head that I've seen on many exams is you're going to pair up, let's say you're going to have a co-ed basketball, a doubles 2-on-2 co-ed basketball team, little 2v2 basketball team. I keep saying 2v2 basketball tournament. And we have a bunch of guys enter, a bunch of girls enter. And for some reason, this tournament, instead of you entering saying, here's my pair I'm going to play with, we're going to randomly pair you up with pair up a guy, pair up a girl, and pair you together. Well, I want to find the average height of these two players. So assuming that these heights are independent, we can just say that I could just, if I want to find the average height of that pair, expected value of x plus expected value of y, I misspoke. The expected value of x plus y would be the same thing as just expected value of x plus y. Kind of overcomplicated with that example, but basically we can break it apart. Obviously, if it's a plus, it'll stay a plus. If it's a minus, it will stay a minus. And I can just break those apart. So just simply, we'll just add the means. So the mean of the sums is equal to the sum of the means, as another way of thinking about that. All right, then what about the standard deviation? Well, I need to find the standard deviation. I actually need to find the variances first. So, and also we have a stipulation. It does need to be independent. RV is short for random variable. So our random variables do need to be independent of each other. If they're not independent, then the math is a little bit more complicated. It kind of looks like the law of cosines. You're gonna have to like add this product of something called a covariance. It's beyond the scope of the course. We don't have to worry about this. So we have to make sure that it's independent. So here's this rule. It's great because if you've listened to any part of me, you realize I tend to ramble and say a lot of words, but I love this rule because it's simple. It's just two words, and both words are equally important. So the addition rule for variance of independent random variables, it's just this, variances add. So both of them are important. Let's talk about the addition part first. So notice in this rule, the variance of x plus or minus y. So if I'm going to take x and add it to y, or take x and subtract it and then subtract y, I don't care whether you're adding or subtracting, it will always, 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 always be a plus on the other side here. So let's talk about this logic. So suppose I'm in a classroom full of students, and I hand everyone a standard sheet of paper. This is notebook paper that I'm picking up for some reason, but so it's just a standard piece of printer paper. Standard piece of printer paper. Its height is 11 inches tall. So I hand everyone a piece of paper, a ruler, and some scissors. And I say, okay, everyone, as accurately as you can, measure and cut off 1 inch off that top. So you should be left with 10 inches. Well, first, for starters, do we agree that all those papers, in theory, should be 11 inches, but at the micron level, if I took a laser to try to figure out the height of those pages, they would all be real close to 11, but a little bit of wiggle above or below that 11. But then when we as humans try to measure and cut off 1 inch, and then I go around and accurately measure how tall all of our pages are, on average, it should probably be 10 inches, but some students might be a little bit bigger than 10. Some students might be a little bit less than 10. Some might be pretty close, but it's going to have a little bit of wiggle. Notice I subtracted an inch, or on average an inch, but I introduced some wiggle. What if I said, okay, I do it again. Everybody measure and cut off an inch as accurately as you can. Well, I'm introducing even more variance, even more kind of chaos. You can think about it. There's going to be even more wiggle. If I subtract another inch, even more wiggle, another inch, even more wiggle. So every time I'm subtracting on average an inch, I'm introducing more and more variance into the situation. So I can never, if I'm subtracting something or if I'm adding chaos into a situation, that's never going to make it be more consistent. It's always adding more uncertainty, more variability. So that's one part, is that variances add. So we're always, always, always going to plus. Other just logic thing is, there's nothing too special about x and y. It could be x plus y, x minus y, x plus y, y plus x. If it was minus, the order does matter. But if for some reason I did x minus y and this was a minus over here, very well, this could be a bigger number, right? And I might subtract. If y is more variable than x, I'm going to end up with a negative value, and that just logically doesn't make sense. We cannot have negative values of spread. So also, it doesn't make sense to have a negative because we can't have negative values of spread. That the negative measurement of width doesn't make sense. All right, so we got the add part taken care of. Let's talk about the variances part. At the end of the day, this is a squared deal. This is a squared situation. I want to recall your memory about the Pythagorean theorem, and I call this the Pythagorean theorem of statistics, kind of coming from here. So recall if I have a 3, 4, 5 right triangle, I could use the Pythagorean theorem to find one of the sides if I didn't tell you what one of the sides are. Let's say I didn't tell you what the 5 was. Well, I could replace the A, the B, I could replace the legs of the hypotenuse 3 and 4 with their numbers 3 and 4, and I can replace the hypotenuse C with this 5. And let's say I wanted to just get rid of these squares, so I could square root both sides, and I had the square root of 5 squared is just 5. But look on this left side, the square root of this is still 3 squared plus 4 squared. I can't just cancel out those squares. That's not a thing because of this plus. Order of operations tells us I need to add these numbers together first. So we get 9 plus 16, or 25, which gives us the 5. Because this should equal, because we do get 5. Notice if I tried, here's a what not to do example under the black line. If I try to break the square root and take the square root of both of them, where I'm just adding this 3 plus this 4, notice I get 7, not 5. Okay? So we have to add squares first, then square root them. So if I have things in the squared world, kind of like this, I have to add them first, then square root them. Another reason why this works with the Pythagorean theorem of statistics is because with this being a right angle there, we can just use the Pythagorean theorem. If we didn't have this right angle, if there's at some sort of slant, this wasn't right, then we would have to use the law of cosines, which again, I said then when it be then that would be a visual example of it not being independent, and then we would have to be using something called the covariance to adjust it, which again is beyond the scope of this course. So we have to add them as variances, and we have to add them. So we have to add them at the variance level, and they have to add. So for example, this is an example of where instead of having an x and a y, like a guy's random height and a girl's random height, this is we're going to be doing two different bets, but they're still corner bets. So I'm going to put down a bet. The round's going to happen. Then we put down another corner bet, and the round's going to happen, and we're going to see what our average and standard deviation are. So the reason why because I'm repeating the same process, I'm going to put a subscript down because this outcome doesn't have to be the same outcome as this. I know I might lose, it might be a -1, or I might win, it might be a +8. They both could be a -1, they both could be a +8. One could be a -1 and +8. This one could be a +8 and then a -1. Those are those four options. It's going to occur randomly. We don't really know which one. Compare that to this one. This is the same bet. I'm just going to then double it. So if I lose, I'm going to get 2 times -1, which is a -2. So I'm going to lose $2. If I win, I'm going to get 2 times 8, which is 16. So I'm either going to, in this case, end up with losing 2 or gaining 16. But down here, I could lose 2, I could gain 16, or I could, what would it be, 7? I could lose 1 and gain 8, so it'd be 7. So do you see how this is a different situation? Okay. But interestingly enough, the expected value is the same because I'm going to have the expected value of x1 plus the expected value of x2. I can just break this plus apart into two different instances of it. And we know the expected value of x1 will just be the expected value of x, so that losing a little bit more than a nickel. And then I'm going to add another losing about a nickel, and we get that losing a little bit more than a dime, which is what we saw a second ago, but a different process. But notice the measurements of spread are different. So here, I have the variance of x1 plus x2. So with it being at the variance level, we can do it, and we need to make sure that it's a plus. We already know what our variance is, so I can just replace those values and add them up. Well, how do I find the standard deviation of this? Notice I did not have a rule that shows me that I can break the standard deviation apart. I cannot break the standard deviations apart because that would be too many words. Standard deviations don't add. That's 3 words. Only 2 words. Variances add. So I have to do it again at the variance level and basically take all this math that we just did and sub it in here under the square root. So the standard deviation of x1 plus x2 is the square root of the variance of x1 plus x2. We just found that to be 15-ish. So the square root of that 15-ish is 3.906. Notice this is a whole lot more consistent. I mean, it's still highly variable, but a whole lot more consistent than what we saw earlier. Let me help you visualize that. When we did I pointed this out a second ago in words, but now it is visually. If I did a $2 corner bet, again, we're going to get 16 or -2. There's going to be, technically, there would be 4 ways to get the 16 and 34 ways of getting the -2. I just didn't draw it to scale, but so this is a way taller than this. So a whole lot more options to get -2 than the 16. Versus x1 plus x2, again, there's some ways to get 16. There's some ways to get -2. There's more ways to get the -2 than the 16. But there's also a good bit about ways to make 7. This pile is actually a little bit smaller. This pile is also a little bit smaller, and this thing that was nothing has now grown. Okay, so that's where you can see that on average, it's going to be the same average. If I found the average, which is what, a little bit more than a nickel, so it's going to average, or a little bit more than a dime, it's going to average about here. Well, actually probably a little bit closer. There's my balancing point. I'm going to have the same balancing point on these two, but the amount of spread on this is a lot less than the spread on this. All right, let's take a look at 2 examples. So given independent random variables x and y with means and standard deviations as shown, we're going to find the mean and standard deviation of each of the variables in the following parts. So they give us the mean, the standard deviation of x and y, and I've gone ahead and calculated the variance. Well, not really calculated, just wrote down what it would be. So if the standard deviation is 14, the variance would be 14 squared. I don't care what the number is. I'm just writing a square on it. Again, 2 squared obviously is going to be 4, but I'm just going to say it's 2 squared because these are my variances. I'm just squaring the standard deviations. All right, let's find the mean and standard deviation of the random variable x minus 29. I know this is no context, but so we're going to have, there's some random variable x that on average gives me 100 and has a standard deviation of 14. So every time that happens, we're going to subtract 29. So when x happens, subtract 29, write that down. X happens, subtract 29, write that down. Do that over and over and over again. What's that average? What's that standard deviation? So on average, we're going to get 71. Here's the logic behind that. So we go, okay, well, I have the expected value of x minus 29. Well, I don't know what the expected value of x minus 29 is. I do know the expected value of x, if only I could get to that. But we do have a property that says if I'm adding or subtracting a constant, I can just pop that out for my expected value. So I'm just going to pop out that minus, and I have that minus 29. I'm going to go back up to it so we can see it. It is this. So notice it does have plus or minus, and those plus or minuses are respective. And so we end up with that plus or minus c. It's a minus 29, so we can get that minus c. So then we do know expected value of x is, it's this 100. Sub that in, 100 minus 29 is 71. All right, what about the standard deviation of this? Well, if I'm always just subtracting a constant, that's not going to change the measurement of spread. It's going to stay the same. I know that throws some students because you're like, but I'm subtracting 29. Yeah, I'm subtracting 29 from every possible outcome of x. Every possible outcome of x is 29 values smaller, but it's not any more spread out. Sometimes when I talk about measurements of spread, I think about spreading jelly or jam on toast. So I've just taken my jelly, spread it out on my toast, and then taken that toast and moved it 29 centimeters over on my counter. Its position has changed. Its balance point is different, but it's not any more spread out. All right, now I'm going to take my random variable y, and for some reason we're going to multiply it times 0.6. So on average, what would that be? Well, on average, it's going to be it's going to end up being 12. But how do we do that? So we have the expected value of 0.6 times y. Well, I don't know what that is, but I do have a property that says if I have a constant times a random variable, I can just pop that constant out and multiply it. So I have 0.6 times expected value of y. We know the expected value of y is 20, so 0.6 times 20 is 12. What about our standard deviation? We said that we know that rewind. We don't know what the standard deviation of 0.6 times y is, but we do know that I could pop the standard deviation, this 0.6 out, this constant out, as long as it's a positive, or make it a positive through the absolute value. So now we just have 0.6 times the standard deviation of y. Good for us. We know the standard deviation of y, it's 2, and so we end up with 1.2. This is a little bit silly, but imagine I have a my toast that I've covered in strawberry jelly, or jam rather, and then I'm going to multiply it times 0.6. It's going to go and shrink up. And suppose also it's on a number line, so it goes, so here's my toast, and it goes and kind of moves a little bit too. So notice if I'm multiplying it by 0.6, it's going to get smaller, it's going to get less spread out. Honey, I shrunk the kids, I shrunk my toast. So it's going to get a little bit smaller. So the spread does change. One little note, remember if for some reason I wanted to calculate the variance, I'm going to need to square that constant that I pull out. And so it would be 0.6 squared times the variance, which is now this standard deviation squared, which is 2 squared, which is 144. Notice this is 0.6 times 2, both of those squared, or 0.6 times 2 squared. So if I just, obviously if I square root, so if I take this, and obviously if I square this, I will get 1.44, or if I take this and I square root it, then I'll get the 1.2. I was a little unclear a second ago. If I take this 0.6 times 2 and I square it, notice it equals this right here. I could kind of air quote distribute that exponent across multiplication and get 0.6 squared times 0.62. So all those things are connected. All right, what if I'm adding x plus y? Well, if I'm adding x plus y, we have a property that says expected value of x plus y. The expected value of the sums is equal to the sum of the expected values. So we have the expected value of x plus the expected value of y. I know what those are, 120. We can add them up and get 120. All right. Now let's do this standard deviation. I have this worked out below because we need a little bit more room for that. All right, so I need to find the standard deviation of x plus y. Well, I recall that I need to do that at the variance level. So if I keep this with the standard deviation, this is going to be the standard deviation of x plus y is going to equal to the square root of the variance of x plus y, because I have to do this as a variance. So I'm going to do my variance work over here. I'm going to pop over here, do my variance work. So our variance of x plus y, I know that we have a property that says I can break this apart because it's a variance and make sure this is a plus. Even if this was a minus, this would be a plus. So I have variance of x plus the variance of y. My variance of x is the standard deviation squared of x, so 14 squared. Variance of y, 2 squared, as we wrote down up here. So I'm going to replace my variance of x and variance of y with 14 squared and 2 squared respectively. Square and add them up and we get 200. So the square root of 200 is about 14.14. So that's my standard deviation. What about if I did the mean and standard deviation for x minus y? Well, the mean is a little bit different because now I'm subtracting, so I'm going to subtract it right here. But then what about what's going on over here with this? Subtract it, and then we get that 80. My brain went ahead of me, so we get that 80. But then what's happening with this? So if I have the standard deviation of x minus y, that's going to equal to the square root of the standard deviation of the variance of x minus y. Well, our property up here says, I don't care whether it's a plus or a minus, it will always be a plus because our rule is variance is add. We have to do it at the variance level, and we have to add them. So we have to add our variances. So notice it's going to equal the standard deviation of x minus y is going to equal the square root of the variance of x plus the variance of y. Gasp. We already know what that number is. It's this. That's going to be 200. So when I plug it back in, we're going to get with the square root of 200 is about 14.14, and we get that. So notice I don't care whether I'm adding or I'm subtracting, the expected spread is going to be the same. The center is going to be different, but the spread around that center is going to be the same. All right, let's take a look at this last example here. At a casino, people play the slot machines in hopes of hitting the jackpot, but most of the time they lose their money. A certain machine pays out an average of 82 cents or $80.82 for every dollar played, with a standard deviation of $90. So I'm just going to kind of go ahead and write down my given information. So I'm going to go ahead and define a random variable x as they've defined it as the payout. The machine pays out an average of 0.82. So I'm going to define x as the payout per $1 played on a $1 slot machine. So the expected value of x is $82.82 or 82 cents, and the standard deviation is $90. So the payout is only 82 cents for the player, though they paid $1, so they're really losing 18 cents. But the spread is 90. Why is this standard deviation so large? As you can see, our answer here, it says most players will lose their money, but a few large payouts are expected. So typically you're going to put in $1, pull the lever, things are going to spin, nothing happens, you just lost $1. You do that, oops, you lost $1. Do that, lost $1. Maybe, oh, something lined up right, and it'll spit $5 out. Woohoo. Every now and then the payout will be huge and large, hundreds of dollars, thousands of dollars. But more often than not, it's a loss. They're quick, easy games to play, and there's lots of them. That's why the casinos love them. And you're always one little thing away from maybe a win, but on average, you're losing about 18 cents, or at least according to this problem. All right, so if a gambler plays a $1 slot machine 4 times, what's the mean and standard deviation of the casino's profit? Oh, they kind of played a little switcheroo on here. They're not finding the mean and standard deviation of the expected payout, but we want to know the casino's profit. So I'm going to redefine a new random variable. I'm going to define a random variable P for profit. So we have our casino's profit on a $1 slot machine. Well, if X was the payout, that's how much spits out of the machine that ends up in the player's bucket. So whatever that is. So imagine that if the player puts in $1 and then it spits out nothing, well, the machine just won $1, so I need this to be a positive 1. So if I do 1 minus the payout, I would get 1. That's right. So if I do 1 minus the payout, I would at least get the positive one that I want. Well, if for some reason the player got lucky and it spit out $10, the player paid $1, the machine spit out $10. Well, the casino just lost $9. So on average, this casino lost, not on average, in this case, the casino lost 9. All right, that makes sense. So I can do that. So this is going to be 1 minus the payout is going to equal the casino's profit. I'm going to rearrange this so that way I'm not dealing with subtraction because that hurts my brain a little bit sometimes. I'm going to think of this as a -1 times my x plus 1. All right, now that's not this question because this question is 4 times. So, but I want to go ahead and define what is the expected value of this p and the standard deviation of that p. So as a bit of an intermediate problem. So the expected value of this p, so I want to find the expected value of the casino's profit. I don't know what that is. Now, you heard me whisper maybe a second ago. I said, on average, you're losing 18 cents. Like whispered that a second ago. So that means on average, the casino is gaining $18. 18 cents. That should be kind of intuitive, and it might be kind of intuitive that the standard deviation is still 90. But I'm going to make sure that we're clear as to why. Right? So this might be a little bit of an unnecessary step if it's kind of obvious to you, but here's the math why using the properties we just learned. So I want to find the expected value of p. I don't know what that is, but I do know we just defined p to be -x plus 1. -x plus 1. You could do 1 minus x, but for our properties, this kind of makes a little bit more sense to view this as a -1 times the x and then add the 1. All right, so I'm going to do with this adding a constant. So if I'm adding a constant, our property says we can just pop that constant out for my mean, for the expected value. So I'm going to pull that plus 1 out as a plus 1. And then this negative right here is really times a -1. So if I'm multiplying by a constant, I can just pull that out as multiplication. So I can really have just negative times the expected value of x plus 1. Well, what's the expected value of x? That's that $0.82 or 82 cents. So the casino is on average losing the 82 cents that's being returned to the player, but they're gaining the dollar that they put into the machine. So that's why on average the casino's profit is 18 cents. They're never actually gaining 18 cents because they spit out whole chips and those whole chips are worth $1, or if it's on the digital card or whatever it is these days. But on average, in the long run, every time that lever is pulled, they're gaining on average 18 cents. Then and again, you might be thinking to yourself, well, how do they make money? Because they have hundreds and hundreds of these and they're being used all the time. And they have ones that are worth more than $1 too. All right, so what about the standard deviation? Well, again, I don't know the standard deviation of p, but I do know that p is -x plus 1. And let's do with this plus a constant. If I add a constant, we've discussed how that doesn't change our measurement of spread. It's still going to stay the same as whatever it was before, right? So that plus 1, it's kind of hurts our math brain because it just goes away, but it basically just goes away. And then what about this negative? Well, if I'm multiplying by a number, I'm going to pop it out of the standard deviation, but make sure to absolute value it. And what's the absolute value of -1? Positive 1. So we just have the standard deviation of x. So notice that the standard deviation of p of the casino's profit is the same as the standard deviation of the payout, which is $90. Therefore, the variance of p, if I square this, is the 90 squared. I'm not going to worry about what that is. I know what it is in reality, but I'm just going to leave it as 90 squared. All right, so now that we know the expected value, the standard deviation, the variance of p, we're now ready to answer the question, what happens if I do it 4 times? So if I do this 4 times, so just to be clear, I'm doing 4 spins. I'm going to call it P1, P2, P3, P4. Sounds like my nieces and nephews from my oldest sister because that's their somewhat nicknames because all their names start with a P. So P1, P2, P3, P4. If I'm going to then be adding up that total because all of the casino's profits would be adding into their total together with that. The reason why I have these subscripts is because those outcomes are different. The player could lose, player could lose, player could win, player could win just a little bitty thing or something. All right, so all of them could be different. So I'm going to find the expected value of that. So if I have the expected value of these 4 different random variables, even though they're related, but they're different. And again, there are different spins and each spin is independent from the other. It's going to be the expected value of P1 plus expected value of P2 plus expected value of P3 plus expected value of P4. Now, if I was to sub in a number, I would just sub in 0.18 for each of these because they're expected value of my P basically. So they're all really going to be the same. But I want to see a pattern, so I'm going to go ahead and re-express it as just expected value of P. I know it might seem like a silly step to have here, but it matters for the standard deviation that we do it this way. So I'm going to model it the same way for the expected value. So this is going to be the same thing as the expected value of P. We know the expected value of P is 0.18. So I'm going to replace expected value of P with 0.18. So it's going to be 4 times that, or 72 cents. All right, now for the standard deviation, I'm going ahead and working it as a standard deviation. Honestly, if I'm working it by myself, I'll start with, I won't do this because I don't like working with everything under giant square roots. It really bothers me personally. I would just work it as a variance, and then once I get the variance number, I would then just to the side, then just do the square root of it. But as one big problem, I want to find the standard deviation of all of this. So again, it's not standard deviations add, that's too many words. It's variances add. So we need to do this at the variance level. So I'm going to have this be the square root of the variance of all of these. And I can break apart the standard deviations now as as a sum of these individual variances. Well, these individual variances will end up being the same value when I do my substitution because they're all from the same random variable. So I can go ahead and summarize this as 4 times my variance of P. We know our variance of P is 90 squared. So here's my substitution with a highlighted green. Then really honestly, I would probably just jump from here to the square root because the problem's not asking for the variance. So I don't care that the variance is 32,400. I just want the standard deviation. So I'm going to square root that and I end up with a nice 180 because this ends up being a perfect square because both of these are perfect squares. Note, it is not 4 times 90. If we had, for some reason, if there was some multiplier on this casino machine that it's like, well, I can push a button and drop in 4 chips, 1, 2, 3, or $4, 1, 2, 3, 4, $4 at one, and then pull, and it's going to do whatever I get, and it's going to multiply it times 4. That would not be this problem. That would me being 4 times 90 for my standard deviation. Notice it's really just ends up just being 2 times 90, not 4 times 90. Okay, and that's because variances add. It is technically the square root of the repeated number, which would be a thing you could know if it's repeated, but I don't have that as a special rule because we just keep our rule as this generic, oh, it was way up here, as a generic thing because they could be completely different values, but we notice with just x and y, but we notice that if it is this kind of repeated situation, we could save ourselves a little bit because look at the next problem. The next question says, well, what if gamblers pay $1, play the $1 slot machine 1,500 times in a day? They just sit there, put the quarter in, or put the dollar in, pull a lever, wait for the result, put the dollar in, pull the lever, and they do it over and over and over and over again, 1,500 times total. Well, what do we expect that to be? Well, I don't want to write P1 plus P2 plus P3 all the way up to P1500. Well, actually I can this way, P1 plus P2 plus ... plus P1500. So imagine I have 1,500 P's. So if I'm adding up those 1,500 P's, the expected value of that is going to be, well, I'm going to have 1,500 expected value of P's. So that's going to be 1,500 times 0.18 or $270. So if you sit there and play on this particular machine 1,500 times, on average, you've just given the casino $270. Congratulations. The standard deviation for it, though, is then going to be this. Again, at the variance level. So we noticed this kind of pattern here that I had 4 different P's. So I was able just to say 4 times the variance. So we can actually do that. There's 1,500 of the same variance of P's. So 1,500 times 90 squared ends up being this. So that is a bit of a shortcut when there are these repeated things. So it's good to kind of see that pattern. If you want to write it as a general rule, feel free. Or just, I personally just like to understand this process to be able to see how it speeds up. All right, so I hope this helped you understand how we can manipulate random variables a little bit better. I don't say this all too often, but feel free to like and subscribe. Thumbs up it if you did. If you did like it, hope this helps, and I will see you in the next one. Bye.